Welcome to the Unboxing Technology series by Digitarati. This video is on Kafka.
Why Kafka? Why not I go with the conventional way of using JMS or ActiveMQ based or AMQP or any other messaging platforms, etc. Why should I be using Kafka? This is one of the fundamental questions. Second important question which people generally get is, so if I, they tend to, this term called microservices has been blown out of proportion. Most of the people think microservices are nothing. Most of the people, sorry, can I request everyone to put themselves on mute? Yeah. So most of the microservice architecture, people think that the moment you reduce the cohesion unit of a service, it becomes microservice. Meaning, the moment I start reducing or narrowing down the scope of a particular service, it becomes microservice. Or the moment I put it on a particular platform or a cloud-based solution, the service actually becomes microservice, right? Again, I want to highlight, I wouldn't want to go into the details during this course of the session today on how Kafka actually relates to one of the critical piece of microservice, right? How, or rather, I shouldn't say Kafka. How is this event-driven architecture very important for developing a properly designed microservice architecture? So these are some of the areas we'll be talking about today. In addition to that, I'll also show how a kind of a mock implementation of this architecture, if I have to bring it about in a standalone program. I've tried to create a standalone program, set up standalone jobs to just show you how this architecture will fit into it. It need not be a full-blown web services, etc., but I'll try to give you an idea of how it fits into using a standalone job. Okay, so first, event-driven architecture, right? This is something which we already know, or most of us already know. So when people say event-driven, they talk about essentially two things. One is on the services side, the event-driven architecture, or on the presentation tier, when we use technologies like Node.js or non-blocking UIs, etc., they call it as event-driven, right? But we are talking about the first part here, right? On the services side, how is this event-driven architecture relevant? Now, when we talk about event-driven architecture from a services standpoint, what we in essence say is that in an enterprise landscape, we might have thousands of services, right? All these services need not be in a single geographical location. It can be in multiple geographical locations, spanning across multiple departments, and each and every department does not know about each other, but still, they would want to consume the services of one another. For example, there might be a service called employee, which might be communicating with the service from HR for fetching certain information related to the payrolls, etc. Right? Even though employee services and HR services are standalone services, they tend to communicate on some key important information which are which overlap. Now, technically, what they call them as microservices, right? They call employee, the moment you start splitting them into multiple functional components or technical components, they become microservices. In this case, employee service in itself will become a microservice. The HR service in itself will become a microservice, right? But the important piece here is that we need to understand that the services will become micro apart from all the features we are talking about. The granular the services are, the highly available component the services will have, the way in which they are independently deployed, all these features of microservices. One of the key important principle we need to understand in terms of microservices, how much coupled they are. They cannot be tightly coupled with each other. They have to be loosely coupled. The more loosely coupled the services are, the more microservices they adhere to the microservice architecture. That is very, very important. I know that there has been implementation of services out there where service one talks with service two. The coupling, even though they call themselves as microservices, the amount of interaction which happens between these two services is so much coupled in nature that we cannot in essence call them as microservices, right? So it is very, very important that we bring in this loose coupling between the services, uh, you know um, uh, in order to make it more micro in nature. Now there is an argument which will come into picture, which is how come a service can be totally standalone? So there is an employee service, there is a payroll service. How can they be totally standalone? They cannot be. Now, as I mentioned, that the employee needs to fetch the payroll information. There is some essence of coupling. Now, it is not about the data coupling we are talking about. We are talking about the process coupling. So I know that we know that the employee needs a payroll information. The question is, how is this employee service going to fetch this information from the payroll? Is it going to be a direct synchronous call, or is it going to be asynchronous, or some other way? How much coupling is there between the employee service and payroll? Now, tomorrow, if the payroll service is going to change, will my employee service needs to change accordingly? If the payroll service is going to be changed at that point of time, when the deployment of the payroll service is going to happen, can the employee service still work or it cannot work, etc. Now, these factors will determine how much coupling from a process standpoint is there between these two services. What event-driven architecture, in essence, brings onto the table is it provides a lot of decoupling out there so that the services can be independent per se. When I say independent, really independent. It is not what we have in most of the architectures today. They call themselves independent, but if service one is down, service two is not accessible. That should not happen, right? So this is a very, very important piece from an event architecture standpoint. I don't want to go into the actual textbook definition here, but I want you to understand this concept. Event-driven architecture, what it tries to bring on the table is tries to decouple the systems. But how? Each and every system, whether it is service one to service two or a totally different third-party system with our own internal services, between the services or between the systems, the communication will happen through events only. It will not happen through synchronous call or API calls, etc., etc. The services between the services will communicate with each other in terms of events. They either emit an event with key metadata or they consume the event for processing. These are the two important pieces in an event-driven architecture. Okay, there are other parts of it, but for the sake of this discussion, let us restrict ourselves to these two important components. Okay, now in a real-time scenario, you can assume most of the organizations will have a notification service. The notification service can be an SMS notification or an email notification, or it can be even a what do you call in today's world, the mobile app notification, push notifications. Now, if you look at it, all these notification services, they will be standalone in nature. They don't care about whether the notification being sent is for a payment or whether it is for a customer acquisition or whether it is for a bill related notification. They don't care about any of it. What they care is the moment an event comes to them with information related to the customer, what type of notification needs to be sent, what is the email address of the customer or a phone number of the customer. These are all the metadata which the event is filled with. The moment they get this event metadata, the notification service will trigger a notification. That's it. They know to consume an event, they know to trigger a notification. So this way what happens is the notification platform is totally decoupled from the rest. Okay, they are not coupled in any way with any of the existing services. Okay, I think you guys are able to understand the idea, right? Now, the non-event driven ecosystem. Now, when I say non-event driven ecosystem, I'm not going back in time, say 25 years. Now, I'm just talking about 5 years old or 4 5 years. Even the moment we started talking about microservices, and people say that their ecosystem is based on microservices. If they are not using a event driven architecture, there will be few issues. Now, one of the primary issues will be because because there is a process related coupling between service 1 and service 2, it comes with a baggage, the baggage overhead. What is that overhead? The moment you have even a single bit of coupling between the two components or the two systems or the two services, the first thing which will get impacted will be scalability. Because the moment you have a coupling, the system with which you are integrating, that becomes a bottleneck, right? So you might have a system which is like scalable to 20,000 users, right, at any point of time. But the system with which you are integrating is scaled only to 5,000 users, then that is your bottleneck. Then your system will not be able to scale to 20,000 because of the bottleneck you have. Right? That also applies to the availability. The availability will get cascaded. The system which has the maximum bottleneck, that availability will get cascaded to the system which has more availability, right? So that is one of the other issues. In addition to that, we have other set of issues as well, but let us not go into those. And another important NFR, that is non-functional requirement, which tightly coupled the system, which is, when I say tightly coupled system, they are still based on microservice architecture, but they are not completely event driven. In that case, what happens is that will also in a way impacts the maintainability and manageability of this. Now, I am sure you guys know the difference. When I say maintainability of the code, it is in simple terms, the development team which is supporting the service or the product which has already gone live, you can talk from their perspective. So they have to make changes to the systems, they have to make updates to the systems, they have to implement a new change request, a new feature into the system. How easily they are able to do is called maintainability. Manageability is from an operation team's perspective. Operation team is always worried about the stability of the system. If there is a change, how stable the system will there be any issues, those kind of stuff. That in umbrella terms is called manageability of the system. So the moment you have a non-event driven based system which is having a kind of a coupling with each other, you are also impacting the maintainability and manageability of this. Okay, so this is very, very important. So I'm going to ask you a kind of a contextualized question in today's world, right? So let me ask you this question, and then I'll tell you how this is relevant to what we are discussing. So, two use cases. So I'm saying that the government notifies that a vaccine is available at all centers in Chennai. This is one statement. The other statement is government issues orders for compliance to SOPP during lockdown. Can pretty much right, but let me just tell you how is this related to Kafka and what we are talking about. The first thing is very important. The first thing is what we are saying is the government notifies that the vaccine is available at all centers in Chennai. Now remember this. Government is just issuing the notification. Government is not expecting any action at all in the first statement. They are saying that the vaccine is available. Okay, people go and get vaccinated, that is a different thing. They don't get vaccinated, that is a different thing. But government is not expecting any outcome of this first statement. They are not expecting any kind of a kind of an action item from this particular statement. But in the second statement, government is expecting an action, which is government is expecting a compliance to the SOPP during the lockdown, which means after the statement, the government is expecting that the people don't just wander around, the law agency take over if in case people. So there is a kind of an expectation from the government after the statement. Now, these two important things are broken down into what we call in an event-driven world or a non-event driven world, right? The first one, you can assume it is an event. The second one, you can assume it is a command. So usually people tend to get confused between the two. Event is something where I'm not expecting any outcome. The moment I publish an event, the event goes out, that's it. I don't expect any outcome. I don't expect any action item on that. But the moment I issue a command, I'm expecting a response based on the command. Right? So this is a key difference between an event and a command. Now, when we are making in a plain terms, when I'm making a web service call, right, a method call, a service call, a synchronous call, or an asynchronous call, right? When I say asynchronous, a method with callback, whatsoever, right? So in all those cases, I'm expecting some kind of a response. The moment I make a request, I'm expecting a response. But when we are talking about events, I'm just sending out the message saying that something is there. In this case, government notifies that the vaccine is available. That's it, nothing more. I'm not expecting any kind of outcome. We are in here talking about the first one. We are talking about events. We are not talking about command, right? Now, this is very, very important. First, what I'm going to talk in the next, this particular slide is the key important time patterns which are relevant for Kafka, which are also relevant to be followed for any kind of an event-driven architecture. Now, the moment you start using Kafka, Kafka actually implements some of those, but not everything is available in the products. Some of them we have to take into consideration when we are implementing an event-driven architecture design. So, the first important thing is event notification. Event notification is very simple, where a service is going to just notify an event. Say that service is like, for example, employee service. When a new employee joins an organization, I just want to broadcast a message saying that, an employee is joined. I give the name of the employee, the email, contact, which department, etc., etc. I put everything into a kind of a message, into a plain old JSON or an XML. I just publish that information to everyone. Now, I don't care what they are going to do with that message. I don't really worry about it, right? So as I mentioned, the first one, I don't really care. I'm not expecting any kind of a response to that message. Now, the problem with this approach is, the moment I start, I put some basic information like employee ID, employee name, employee email, and then I publish this message. Let us say a payroll. There is a service which will actually calculate the payroll. Now, for calculating the payroll, I don't have sufficient information here. So I just have employee ID, I have employee name, employee email, that's it. But I also need to know his position, what is his designation, what is his pay grade, etc., etc. What was the, all the other information, what, what designation he is in the salary band, etc. I don't have that information. Now, in order to get that information, what the payroll service will do is, it will take the employee ID, it will query back the employee service, some other service inside the employee service is deployed to fetch the pay grade or designation, some kind of an information which the payroll service is required to calculate, needs for it to calculate the payroll of employee month on month or whatever, right? So there is a need for the payroll service to call back. So this is a problem, because whenever we say event notification, what we are saying is we just publish the basic information of the event. We don't stuff a lot of information inside the event and publish it to everyone. There's no need, right? Why should I give too much information for an event which is just an information only, right? So, but if there is a requirement where I need to reduce even that level of coupling between the payroll service and employee service, I don't want the payroll service to query back the employee service, okay, because of the overhead involved. Why should the blah 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 whatever, because it is not about one employee we are talking about. There can be hundreds and thousands of millions of employees. In that case, what will happen is the employee service is going to be hit million times. So what we do is that in an event carried state transfer, apart from the basic metadata, we will also add some additional information, right? Additional information to the into the event, so that the payroll service don't have to do a callback to the employee service. So the moment you start stuffing more information into the event, into that JSON, etc., or an XML, it doesn't. We don't really care about the payload format. It could be anything. It could be CSV or anything for that matter. As far as it is able to be read by most of the consumers, we don't care about it. So we stuff most of the information into the event and publish it. The moment we do that, the moment there is no requirement for the consuming service to do a callback, then that particular design pattern in an event-driven world is called event carried state transfer. Okay. Now, so there is a subtle difference, very subtle difference between these two design patterns: event notification, event carried state transfer. The only difference is how much information you are stuffing into the event. Okay. Now, there is one important design pattern in this space where Kafka is also implementing this in a way. Is the problem with the event carried state transfer is that this is a problem, right? So the employee service publishes the event with all the information, including the pay grade, designation, everything, at 10 a.m. But for some reasons, what happened is due to some connectivity issues or some deployments or services down, the payroll service was not able to consume that information at that point of time, right? Then what happens is that event is lost. Or let us assume the worst case. What happens is the entire service ecosystem was down due to some very big outage. Then what happens to the messages which were published during this time? Will they be lost? Right? So it will be lost if we are not storing that information somewhere. Right? The event which got published across multiple services, if that was not being stored somewhere, then definitely that message is gone. In order to address this problem, we go into the next design pattern called as event sourcing. What we do is very simple. Before we publish the event out there into the real world, we will commit that event in our data source. The data source could be database, or it could be Hadoop, or it could be plain log file. In Kafka terms, we are talking about the commit log files. I'll be talking about that shortly. But in Kafka, what happens is the data will get stored locally in a commit log file. So what event sourcing does is it is going to store the event before publishing it across to everyone. But the other important key component here is that event sourcing should be able to, if we are going to say that our system is event sourcing compliant, uses the event sourcing design pattern, if there is a total outage, I should be able to replay the entire message so that my system comes back to the original state. Okay, so that no messages are lost. So the moment you start storing it and start thinking in this way, you can say that we are using this event sourcing design pattern, and I'm assuming that every system which is using the event driven design pattern will do event sourcing in a way, either through using platforms like Kafka, or they will be storing it on their own custom made, etc. Right? This is very, very important piece. And finally, the CQRS is a common design pattern. This is very, very important again. Is the command query responsibility segregation, right? Yeah. So in a command, in a command query responsibility segregation, what we are saying is, on top of event sourcing, we want to bring in some kind of what do you call scalability and availability. I'm not going into the details of this design pattern, because you can actually interpret it in a different format, because CQRS is not only for event driven architecture, it is also applicable for say a conventional RDBMS world, right? So in a conventional RDBMS world, what we do is that in order to improve the performance, scalability, and availability, what we do is we bring in read replicas. Okay, there will be one master server, multiple read replica servers. What we do is that we read from multiple read replicas, but when we commit only to, when we update or commit data, we update only to the master. And RDBM, most of the RDBMS or all of the RDBMS will have a synchronization process between master and slave. In some cases, there will be a minor delay, but most of the cases, what happens, the synchronization will happen within a couple of seconds. So this is called as a command query responsibility segregation, wherein you are segregating the responsibility of reading and writing. You read from one of the node, but you write it back to another node, right? So from a big data world, from a cluster world, you can assume this as when you are using when you are querying for reporting, you use read only cluster, but when you have to update data, you write it back to another cluster, which is write only cluster. Therein, what happens is you automatically get the scale, and also the performance, right? So on top of event sourcing, we can also implement a CQRS pattern in order to improve the respective NFR. So these four important patterns is something which will be obviously be used in our day-to-day implementation of a similar architecture, which is event-driven architecture. So now I'm moving into another important piece, the same direction. When you take a conventional enterprise architecture, now I'm not talking about an on-premise solution, I'm also talking about a cloud-based solution. When you are totally cloud-based or you are having a hybrid architecture, doesn't really matter. But this is what a conventional architecture will look like. So you will have the first layer, the tier one, even though it may not be a physical logic, it can be even a logical tier. It may not be a physical tier. So in a conventional architecture, what happens? There is a tier one, a logical tier one or a physical tier one, then a tier two, which is again a logical or a physical, and then the tier three, which is the database layer.
Recording is
and
on.
Then sorry. Was there a question?
I think you should mute everybody. I think somebody is on mute. That's why you're hearing this.
Okay, so in a conventional architecture, what happens is we have 3 tiers, right? So whether it is on the cloud. So the tier 1 is totally devoted to presentation. It could be web application deployed, or it could be services which are being consumed by other third parties or mobile applications, etc. Now, underneath the presentation tier, we'll have the business logic layer. The business logic layer can be other set of microservices or services deployed by other teams elsewhere geographically, or a third-party service. And then we might have an internal ESB which does all the workflow management or business logic processing, everything. Internally, we will have a messaging tier which will be used by the ESBs or the microservices. And then the third tier will be the databases or data sources. It need not be RDBMS, it can be anything for that matter. So this is the conventional architecture. Now, this is the conventional application architecture, application ecosystem. And then we will have proper monitoring which monitors every piece here. In addition to that, we will have the enterprise data warehousing in parallel, which will be separate from the application in most of the cases, where there will be a data lake as their data source. The data lake the data coming into the data lake can be coming from the data sources via ETL process, or it can be a direct replication where a specific set of clusters can be devoted for data lake purposes. The cluster keeps synchronizing from the actual application data source every now and then, or it can be ETL processes which will be ingesting data into the data lake. And then we will have the ETL processes which reads data from the data lake if there is a transformation required. The data lake is not always data, the database. It can be files also, right? So then what happens is, for our purposes, we need to read the files, do some massaging on the file, do the transformation on the file, and then ingest the data into our own internal data sources inside the EDW ecosystem. And then we have to perform analytics. The analytics can be batch-based analytics, or it can be a real-time analytics also. And then, based on the outcome, we present the dashboards and reports to the users. In some cases, what happens is the analytics can be real-time. The outcome of the analytics will go back to the application architecture, application services, where, like for example, let us take fraud management. Pretty much all the fraud management analytics are real time. So when a customer uses a specific credit card which has been blacklisted, you would want to stop the transaction immediately. So in that case, what happens, the analytics is very much real time in nature, and the response is sent back to the application immediately. Now, this is the conventional enterprise landscape. Now, if I have to put this concept of event-driven architecture on top of this. Now, what are all the problems I see in this conventional enterprise architecture? The problem is that even though the architecture looks like they are decoupled in nature, in essence, they are not decoupled. So, if I am going to, when I say messaging in the application architecture, I am talking about conventional messaging methodologies using JMS. So, JMS and conventional messaging, they are very good, but they cannot, remember, the moment we start queuing or we use any of the JMS, technically, even though it is feasible, the moment we do some tweaking, technically, JMS-based methodologies are not good for volumes. They are not designed to handle high volumes of data. They are good between P2P, point-to-point messaging, In a way, they are good for publish subscribe model as far as the consumers are limited in nature. But if you take any of the JMS conventional frameworks like ActiveMQ, they either go for master-master or a master-slave architecture where the queue will be replicated for high availability. They are good as far as the volume is considerably less. But if I have to introduce complexity, like what I mentioned earlier, like the key second one, which is the event sourcing, the replay capability provided by these messaging framework are very limited in nature. They will not be able to replay messages in the way we want it. Although there we can process messages, but a complete replay of messages is not possible in these messaging frameworks. Another important key piece is that when it comes to volume, they are not built for volume. For example, if I have to bring in an event-driven architecture on top of this architecture, I wouldn't want to, from an EDW landscape, I don't want to read data from my data source on a scheduled basis. My event-driven architecture should be able to take care of publishing events to my EDW. For me, EDW will become a consumer. Just like the example what I mentioned, employee and payroll, my payroll services were the consumers. In this case, my EDW will also become a consumer. I don't have to put some scheduling thing. I don't have to, invest on the resources required for those scheduling, etc. Pull data, all those complexity is removed, because the moment I start publishing notifications, publishing events, all the system available, including enterprise data warehouse, becomes a consumer for me. If a new employee has been created, I publish an event, EDW will take that information and will update that information into its data lake. If a new bill has been generated for the customer, I publish that information, EDW will consume that information and will automatically go and do the analytics required for the bill generation, what's it, etc., etc. So why I am specifically talking about EDW here? There are other applications in any organization, right? Not only EDW. But if you look at any enterprise systems, the EDW or data analytics team or the data science team, they will be separate. They will not interact with the application systems directly. Most of the cases, they will only have scheduled jobs which will be pulling the information from the data sources. Okay, so the objective of this slide is to tell you that with an event-driven architecture, we can bring everyone onto this framework of event-driven architecture, including the EDW, which in most of the cases will operate in silo. With an event-driven architecture, we can bring not only EDW, we can also bring the monitoring. Just think about it. Today's monitoring revolves around monitoring the log files, monitoring the databases. If I have to go further, monitoring the system's performance in terms of CPU utilization, memory utilization, etc., etc. If we are going to implement an event-driven architecture, even this monitoring can be brought into this umbrella. Events can be published directly from log files. every time there is an event which happens that can be published, monitoring systems will become consumers. They consume the event and then they trigger the respective alert or notification. On the other side, if a system is down, the monitoring system, the consumer, will not be getting the notification, which in itself will become a kind of an indicator that something is wrong. So they will be able to trigger alerts and notifications. So this is what a full-blown event-driven architecture will look like. Okay, so I think hope, I'm able to convey that idea to you guys, right? Basically, notification service, technically, that is how it is standalone. Today, in most of the cases, what will happen is services will be deployed separately, but there will be an intercommunication between the services through RESTful API call. The moment you have that, what happens is you cannot say that it is 100% decoupled, because there is a process or a functionality requirement where one service has to call another service. And when service 2 is down, service 1 cannot process that data. Right? So that functional dependency is also removed when you have event-based interaction. Right? So you see, conceptually it is a little bit tricky to understand, but we move the entire data abstraction to the MOM. Till now, what we have been doing is we have been dependent on the service invocation. Going forward, we will not depend on service invocation. For us, the entry point for processing will be the event, the message, which will come into our service. We will process the message, we will respond to that message. That's all. Now, I just wanted to clarify one more thing. So, the description looks like we are processing the message and we are not responding, meaning we just say an employee is created, I process the employee and then I store some information onto my table. That's it. I complete the process. It need not be the case in all the use cases, right? We can also have a scenario where an event is published, a fraud management system, that is part of my demo as well today. A fraud management system can actually act on the event and will respond back immediately in real time. If this was a conventional system, the fraud management system would have exposed a RESTful API. The frontliner system would invoke the RESTful API and will be waiting for the response from the fraud management system. And the fraud management system will be responding with yeah, it's a fraud or it is not a fraud. And then based on that, the frontliner system would have shown an error message to the customer. But what I'm saying here is the same scenario can be replicated using event-driven approach without a RESTful web service call. That is what we call them as a bidirectional communication, bidirectional event, where an event is published and a response is also given back for the frontliner system to process and show an appropriate message to the customer. We'll jump into Kafka with this background, right? This background is not sufficient, but for the sake of our discussion today, I think we will try to focus on Kafka. I'll keep. I'll talk about Kafka from a systems from a systems perspective, which we already know, like the queuing systems, etc. So, Kafka, one of the key differentiator of Kafka with the conventional queuing system is its distributed platform, right? So Kafka is distributed. That automatically gives us the advantage of scale availability, and then in terms of failover processing, etc. So Kafka by default gives us the advantage, right? Uh, Another important key piece is because it is distributed, we have a cluster of brokers. We automatically have the advantage of the cluster spec. So one system can be vertically scaled to only X and X CPU and X RAM. But the moment you have a distributed capacity, you will have proportional increase in your RAM and CPU. So, like what I mentioned earlier, this will give you the advantage of processing volumes of data, large volumes of data, which was not possible in our conventional queuing system. And one important feature of Kafka is they use distributed commit log. Now, this commit log is you can relate this to our event sourcing. So, this is one of the design pattern where before you publish the event, you have to store that information so that in case of outage or failure, you will be able to replay them back. So, Kafka actually complies to this design pattern in a way. So if you are using Kafka, you are complying to this design pattern indirectly. The data, the event, whatever you are publishing, they are stored in log file. This log file is sorted chronologically. So the events are sorted chronologically. If you know the technology of blockchain, we also have the similar concept here. So all the events are tracked in a sequential way based on the timestamp of the event. So this log file will have a complete set of events, whatever has gone through the Kafka ecosystem. If in case there is an outage, for us to replay this entire event will be an easy peasy job. We just have to restore the log, replay the log. All the events will be replayed from start to end. Now, I'm not going into the details of how long you want to maintain the log, etc. Everything can be controlled via configuration. I'm not going into the finer details of it, but just think that there is a log file where every event published to the Kafka by the producer, and before it is being consumed by the consumers, that message is stored internally in commit log files. How this log file is separated, etc. I'll try to give a sense of it shortly. What happens is, there are two things, right? Two important things. Now, how data is going to be stored and how it is going to be published, etc. Now, we are talking only about that part at this point of time. But from a feature standpoint, now internally Kafka is going to have a distributed messaging platform. Internally, Kafka is going to store the commit log. Internally, it is going to have this failover, etc. But it doesn't really matter whether it is an offline or an online batching system. But internally, this is going to be the same for both OLTP and OLAP. Doesn't really matter. Okay. Now, coming to your question on how Kafka is going to, really guarantee message delivery and response. Now, remember, before telling you about Kafka, let me ask you this: in a conventional microservice architecture, in a microservice world, how are we addressing this issue? Now, in a microservice world, we call this as a high availability, requirement, where at any point of time I send a request, I should be able to get a response. Now, how we achieve that is I bring in multiple nodes so that even with one node going down, I will be able to respond back. Now, what we also do in the microservice world is we bring in a queue so that a queue, unless and until you process the JMS message, that message is going to be redelivered to the same service, and then it is going to be processed, and then the result will be responded back. And we also adopt a stateless approach, meaning every request you send will be stateless in nature, so that if there is a 20 node cluster, the message goes to one node, message goes to the 10th node, doesn't really matter at all. Both the nodes are going to give you the same kind of a response. Now that is how we have addressed this issue in a conventional microservice. What we are saying here is nothing changes. We are just going to have the same kind of an architecture. We are going to have, if there are 20 nodes, we'll still have 20 nodes. But what we are going to do is, internally, if we have been using JMS, we just replace that with Kafka. Okay. Now you will ask me, okay, what is the real advantage I get there? Because my services are working fine, right? Now, the advantage is, think that we'll get the advantage only when we start thinking 10 years later as opposed to 10 years before. Now, let me give you a real-time scenario. 10 years before, the type of processing we did on this data, let me take fraud itself. In order to detect a fraud, we would have done a very basic check, just to check whether this number has been blacklisted earlier, saved in a database somewhere. The database server is sitting on a heavily designed spec, like 120 GB of memory and whatnot, 200 vCPU, etc. So the database performance is good. So even with millions and millions of customers, when you query, you get that information. Fine. But looking at what is happening today and 10 years on, the amount of processing which you will be doing for detecting a fraud is not just checking into a database. You will have to check whether the customer is blacklisted. You will check whether this guy has been blacklisted in any of the central agencies, or you will check whether this guy has done transactions in quick successions in the last 5 hours or last 1 hour, how many transactions he has done. You will have to check multiple parameters. Now, you will not be able to do all these processing business logic into your service. Definitely not possible, because you want your service to be lightweight in nature. So what you will be doing is, you will be pushing this processing capability onto your analytics layer. That can be a Spark streaming application which is running, which will do all these quick processing, accessing multiple data sources, will process the information and will respond back within millisecond on whether this customer is a fraud or not a fraud. So, because we are pushing this logic into an analytics platform, you want some tool which will gel with this analytics platform. For example, one of the attribute is Kafka is very much designed to handle large volume of data. Whatever be the data volume, it can handle. So think about this scenario. You have the front-end microservice, then you have Kafka, which your front-end microservice will publish an event to. Kafka will publish an event to your Spark streaming. Spark streaming will do the processing, will respond back to Kafka, and Kafka will respond back to the front-end microservice, and front-end microservice will respond back to the customer. This is the architecture where Kafka will fit in. We are still able to deliver the same kind of a response, same kind of a failover, same kind of a message guarantee, whatever we had before, but now we are able to make it even more effective, even for a large volume of data processing and large volume of payload. I've removed a lot of complexity from this diagram. and I've removed a lot of fine details about the architecture, but to an idea, I'll try to focus on the key points, right? When it comes to Kafka, have the same concept of queuing, which is we have producers, we have consumers. In between, you have the brokers, right? In Kafka architecture, the brokers are clustered in nature. So we have cluster of brokers. There is no concept of active cluster, active passive cluster, going forward. It is all active, right? So when people say active, even in a conventional methodology, whether it RDBMS or queuing, so what happens is one node, there is one node 1, there is node 2. When we say that these are active, which means that if there is 150 GB of data in node 1, in node 2 also you will have 150 GB data, right? There is no kind of split of data, redundancy. The concept of redundancy is not actually maintained there in the, right? So, but when we are talking about all these clustered technology, the data is not fully replicated in all these nodes. There's partial replication. If I have 5 nodes, if I say that the replication factor is 2, the same data set will be replicated in 2 of the nodes. But it will not be replicated in all the 5 nodes. So if one of the node goes down, another node will be able to handle the data loss. If we think that we need increased replication, we have to increase the replication factor to 3 so that we have more replication of the data in the cluster. Accordingly, your size of the the data, the storage will also increase in each of these nodes, but that is up to individual implementation. So the way in which the data is replicated from a conventional architecture of ActiveMQ is totally different in all these distributed mechanisms, whether it is Kafka or Hadoop or whatever, right? That is how it works. So producers will push the data onto Kafka brokers. The data is stored. How it is being stored, I'll talk about that shortly. The data is stored, and then the consumers who have subscribed to the individual topic will be able to get that data, get that event for processing. Now, the terminologies are very important here. When I say producer, producers are those components which will be publishing information to the broker. The producer can be a web application, it can be a standalone Java job, it can be it can be a cron job, anything. As far as they are using the Kafka library, client library, and the producer object, they will be able to publish the data to the broker. On the other side, the consumer can be a web application, it can be a cron job, it can be a standalone Java jobs, anything for that matter. So the consumer will be listening to the topic. The moment a message is published to the topic, the consumer will get that event, will get that message for processing. The message can be a JSON, it can be a string, it can be a CSV, it can be anything. As far as the data is able to be serialized, it should be okay. The brokers are nothing but individual instances of Kafka. So if I have a 20 node cluster, Kafka will be running in all the 20 nodes, but one of the node will be the coordinator or the main node or the master node. The master node has some responsibility, will have some additional responsibility as compared to the broker nodes. we will not go into the details of it, but just think that a master node is the primary node which will maintain some metadata about all the other worker nodes. The zookeeper in itself will be a cluster. The zookeeper here is not going to do any kind of a data processing, etc. The Kafka cluster will be using the zookeeper to maintain some metadata information. The zookeeper will be a kind of a data store for the Kafka to maintain information as to who's the master, who's the worker node, and there's some information like offset, etc., etc. I'm not going into the detail again, but just remember that the Kafka will use zookeeper to maintain some metadata about the cluster, not the business data, but just metadata about the cluster. Okay. Now, inside Kafka, we have to create topics. Topic is nothing but, in a plain RDBMS world, you can imagine topic as nothing but a table. So when I say employee information, I keep that information in an employee table. Payroll, I'll keep it in payroll table, right? Similarly, I will create different topics in my Kafka. The moment I create topics, remember, as I mentioned earlier, the topic will be replicated across multiple nodes. So how does that happen? Internally, what Kafka will do is, this is also not a new term. We are, if you guys are used to advanced RDBMS concepts, you already know what the sharding and partitions are. So in RDBMS world, we have a concept called partition, where the table will be the same but based on some criteria, we will differentiate the data, meaning we will separate out the data. Internally, RDBMS will store partition, even though it is coming from the same table. Underlying the data will be stored in different files. The same concept applies here. Every topic can be separated out into multiple partitions. Okay, for example, inside employee, I will create a partition for based on the department. There will be a development department, there will be a testing department, there will be HR department. So we can separate out the partitions so that the data is stored in different partitions. Now, why do we need to create partitions? Of course, performance. And another important thing is partitions. You can also have some parallelism in terms of processing. So when we process the data, we will be able to parallelize the process, parallelize the consumer process, for example, based on the partitions. So that is partition. Okay. Now, I mentioned earlier that Kafka is going to maintain the messages in a log file, which is called as a commit log. Remember, within a topic called employee, I mentioned that employee topic can be divided into multiple partitions. Kafka will create separate commit files for each of the partitions. So partition, say development team partition will have a different commit file. HR department partition will have a different commit file, etc., etc. And remember, because of this failover capability, the moment you define your replication, these commit files will be in a 20 node cluster, they will be replicated in more than one node. So topic, partition, and commit log file. So these three things are replicated across multiple nodes. To just have a even narrowed down view of it, So inside an individual broken node, you will have a topic 1, topic 2, topic 3, topic n, and within each of this topic, I can have multiple partitions. So partition 1, partition 2, partition 3. All these partitions you will give it at the time of creating the topic. You will define how many partitions you need, etc. Okay. So again, this is even more detailed view of it. So if I have a partition 0, I will have, just think about it as a separate log file. So I'll have a commit log file 0. Partition 1 will have a commit log file 1. Partition 2 will have a commit log file 2. Remember, all these are related to a single Kafka topic. Is that okay? Guys, any questions in this? Oh, one obvious question you might think is, in RDBMS world, I know how to put it into, I know how to put a data into a partition based on a column value. Say if I put a column value as HR, it will go into one partition. If I put a column value as development team, it will go into another partition. Then how, from a Kafka world, how do I know that this data is going into which partition inside the topic employee? The event I publish to Kafka, it is called as a message. Now, message will have a key value pair. There will be a key, there will be a value. Based on the key of the message, Kafka will know into which partition the message will go and sit into. Okay, so that is how Kafka will know where to put the message in. I'll run to, for going into further details, let me show you some code so that we are able to contextualize what we are talking. Okay, let me show you a code. The producer. So what I've tried to do is to show you the conventional way of, or rather I shouldn't say conventional. If I'm not using any framework like Spring, what I would do to communicate with Kafka. But if I'm using a framework like Spring, or for that matter, anything Spring Boot, how will I communicate with Kafka, right? So I'm showing you both. Okay, so from a consumer standpoint, sorry, from a producer standpoint, I need to have some attributes. I'm not going into the details of the attributes. Maybe you can have the details. You guys can refer docs and stuff. But like any other, just like you're connecting with your database, you need connection string, username, password. Similarly, Kafka will require some information. You need to tell where you're going to connect. In this case, I have a local Kafka instance running. So I'll have to say the the IP address and the port number. By default, Kafka's Bootstrap server runs in this port. In addition to that, because it is a producer, I need to say the serializer. In this case, the message which I'm going to publish, the key of the message is going to be string. The value is going to be a string. Hence, I'm using a string serializer. Okay. And then what I'm doing is I'm setting all these properties into a Java property object, and then I'm creating a Kafka producer object to which I'm passing this property. That's it. So my producer is done. You can assume this producer object to be like a conventional RDBMS connection object, Java connection object. Now a connection has been established. Now I need to send information. So I call the send method, which will require us to create a producer record object, which will internally create a Kafka message. So I need to pass a key and a value. Now, in this case, there are a lot of overloaded options which I have. So what I'm doing here is, particular case, I'm passing the key as null, going to pass this information. This is my message. This is my message value. This is mandatory. My topic is also mandatory. So I've created a topic called simple driver topic, and I'm going to send a message called knowledge should be free. A simple message. On the other side, on the consumer side, pretty much the same. I have the properties here for my producer, but on the consumer side, if this is same, the bootstrap server is same, but on the consumer side, we are not going to serialize the object. We will be deserializing the object. There's a vice versa. So I need to specify the deserializer. And then I will have to specify a consumer group ID. I'll be talking about it shortly, why we need this. Similarly, what happens here is I'm creating a consumer connection object by passing all these properties, and then I'm going to print all the information from the topic. Whatever has been published to the topic, I'm going to print it in a loop. I'm going to run this as a loop and just print the value. Going through all the values and print. So, in order to do that, after creating the consumer, I need to attach this consumer to the topic. This is called a subscription. Subscribing the consumer to a topic. So in this case, what will happen is the consumer will get attached to the topic called simple driver topic. Then once it gets subscribed, it is listening to the topic for new messages. So what we do is we run a infinite loop, and we will call this method called poll with a timeout. So what happens is every 10 milliseconds, this poll method will be listening to the topic for new messages. The moment the message arrives, it is going to print the message to the consumer. Okay, so this is a simple way. So let me just quickly run this. My Kafka is running. My Zookeeper is also running. I've attached all these scripts and everything inside the Git folder. One moment. So my Kafka is running locally. It may not have the best performance locally, but it's still okay for demo and other purposes, right? So now I'm going to run my producer. Rather, let me start my consumer first. So my consumer is listening right now, not doing any activity. So the moment I publish a message from my producer, done. My producer is done. So you go there. From the consumer standpoint, you are able to see. So this is my consumer group CG1. I'm able to see the message, but my consumer is running continuously, right? So I can publish one more message from my producer. You see that the other message is also coming through, etc. Right? So this is a plain implementation of producers and consumer. In most of the cases, we use it, but if we are going to use Spring to achieve the same result, lot of things are taken care by Spring, right? Spring Boot. So in my application YAML file, I define whatever properties I define in my Java code, I define it in my property, in my application YAML file. And my code is very simple. So this is my Spring application. And I've defined a sample controller here. And I have my consumer, and so here I've defined it as a service, both producer and a consumer. So for producing the message, I'm using a Spring's Kafka template, and I have done an auto wiring. So what will happen is automatically this object will be created, and with all the properties we have defined in application YAML file, and then I just have to invoke the send method to the topic, and the consumer side I have to annotate the method with, the method should be void. I just need to annotate the method with a Kafka listener annotation, define the topic, and define the consumer group. I should be able to receive the message. Okay. So let me run this. So if I have to run this, then have a controller method. This is we are trying to trigger. We are trying to produce a message from a web. The message can be hello world. So now you should be able to see this. So here we are using Spring's own way of consuming and reading, producing and consuming the message. So it can be anything. Automatically it is getting consumed, right? So this is the Spring way of. So I'll be pushing all this code into GitHub, for your reference. So this is one thing, right? So other part I wanted to run through is before I go into that. So let me just run through. So this will give you a kind of overall picture of all the components inside Kafka, right? Okay, first Kafka message, right? So Kafka message, as I mentioned earlier, it is it is a message which is being produced, right, from a producer. In an RDBMS world, you can assume that the message is nothing but one row in a table. But here, remember that a message will be key. It will always be a key value pair. There will be a key. There will be a value. A key is optional. Value is mandatory. Okay. And then what happens is when we are producing message to Kafka, Kafka will do something called as a Kafka batch. So of course this is controlled by certain configuration. The moment I call send method on the producer, the message is not sent to the Kafka immediately. What it will do is it will wait for a shorter duration of the time, and it will try to buffer all the messages, whatever has got accumulated at that point of time, and then it will send it out to the broker. The reason for doing this is if we have systems which are producing messages in quick succession, there will be a performance issue if I am going to send each and every message individually. Now you can relate this with a batch approach in RDBMS. The moment you enable batching in RDBMS, what happens is you don't commit the records one by one to the table. You group all the rows together, and when you say execute batch, at that point of time, all the messages will be updated into the table in one shot, right? So this is going to give you ample amount of performance. The same logic applies here. Kafka producer will not push all the data one by one to the broker. It is going to buffer and then it will push. Now, how much to buffer, how long to buffer, all these are determined by certain criteria. We have to define some parameters and properties, in our configuration. That is called Kafka batch. Schema. The messages, whatever we publish, the value or the format of the message is totally immaterial to Kafka. It can be JSON, it can be XML, it can be CSV, it doesn't really matter. You know why? Kafka will not introspect into your message. Kafka will store the message as is into the log. And when it needs to consume, if some consumer is calling, it will read the message as is from the underlying storage and give back the message to the consumer. Now, this is one of the key attribute of Kafka in terms of performance. Because it is not doing any kind of processing on the message, we are able to get some performance on the message. Okay, now this is called as a zero copy approach, meaning we just store the message and retrieve the message as bytes. We don't go into the Kafka does not go into the message formats or something. It doesn't do any kind of a processing. Okay. Now topic, as I mentioned earlier, topic is something similar to a table in an RDBMS world. Partition, each and every topic is separated into partitions for multiple reasons, for performance, for parallelisms, in terms of processing, etc., etc. Producer is any component which is using the Kafka CLI of Kafka client library to produce messages to broker. Consumer is any component which is using the Kafka CLI library to consume the data from the topic. Offset. Now, this is a very, very important concept in Kafka. Every message which is written to the underlying commit log will be assigned a unique ID by Kafka. Now, this is very, very important because this is how Kafka will know whether a particular message, you can assume this offset as a primary key in RDBMS world, even though not exactly the same, but somewhat. So every row can be uniquely identified with a primary key in RDBMS world. Similarly, every message can be uniquely identified with this offset. Now, At the time of producing the message, Kafka will assign an offset to the message, which is responded back to the producer if the producer wants it, or it will be inside the commit log. When the consumer is reading the message, the consumer will keep track of the offset, or rather I shouldn't say consumer will keep track of the offset. The consumer will take the offset and it will use a particular mechanism to keep track of the offset in such a way that the consumer knows that the offset has been read. Say for example, a producer is producing a message. That message is going into Kafka. A unique offset ID has been assigned to this message. Let us say number 1. Consumer is going to read this message. But at the time of reading the message, the consumer server has got crashed. Now, how will the consumer, next time when I bring back the consumer servers, how will the consumer know what is the message it read and what is the message it did not read? In a conventional queuing mechanism, what happens is the message will be kept inside the queue. If we have switched the persistence mechanism in the queuing world, like for example ActiveMQ, the message will be kept inside the queue until the consumer will respond back with a commit. The moment the consumer responds back with a commit, the message will be deleted from the queue in a conventional queuing world. But in Kafka, the message will not be deleted. The message will be kept inside the commit log for a longer period of time. So having said that, how will the consumer know? Because here the responsibility of ignoring the duplicate message goes to the consumer. The consumer has to know that it has read the message or it has not processed the message before. The consumer will use the offset in order to know whether the message has been processed or not. Okay, now let me explain it further. Other concept here. There is something called as a consumer group in Kafka. Remember, in my Java code, I mentioned something called as a group ID. This group ID uniquely differentiates a consumer group. A group is nothing but set of consumers which are processing the message. Now, in our example, which we talked earlier, when an employee service publishes an employee event, it will be consumed by payroll. Payroll department consumer. It will be consumed by billing department consumers, etc. Each and every group which is consuming our message, we call them as a consumer group. A HR, the payroll group, billing group. Each and every group, we will have multiple consumers. Okay, so imagine when a message is being published and the HR department has deployed a consumer, it is not one consumer, it will be group of consumers. Okay, because that is how Kafka will manage a scale, parallelism. We will have multiple consumers reading messages at the same time. Together, all the consumers is called as one group. So I can have a HR group consumers, I can have a billing group consumers, etc. All the groups will consume the same message, can consume the same message. But within a consumer group, all the consumers will not consume the same message. Between them, if one message is being consumed by one consumer, that message will not be consumed by the other consumer within the same group. Okay? How is that happening? Within a consumer group, each and every consumer will be assigned to specific partition. For example, if consumer 1 is attached to partition 1, consumer 2 will be attached to partition 2. You cannot have one partition consumed by two consumers, meaning I cannot have C1 and C2 pointing to partition 1. That is not possible. That is how Kafka manages that same message being consumed by two consumers. So that the same message will not end up in two consumers because two consumers cannot listen to the same partition. But vice versa is true, meaning I can have one consumer listening to two partitions. That is possible. Now, as I mentioned earlier, for every partition, I will have one consumer assigned. That technically what we say is that consumer is the owner of the partition. So we call it as a partition ownership. Okay. Now, I mentioned that offsets are unique value which are assigned to every message. Kafka, that is how it uses. Kafka uses this way to deduplicate the messages. Now, where is this offset being stored? Like, for example, there is consumer group 1, there is consumer group 2. They are consuming a message. Now, for some reasons, consumer group 1 collapses, dies. Then when consumer group 1 comes back alive, how does consumer group 1 knows that it has not processed the earlier offset? What happens is, every time consumer reads the message, it completes the processing. What the consumer will do is, it will commit. It will commit the offset along with the group ID. It will say that consumer group 1, or for example in our case, HR group consumer has committed the offset number . Already processed the offset number 1. So even if the Kafka is going to publish offset 1, they will not process offset number 1. They will start from offset number 2. Okay, it is a kind of a tricky topic which requires further discussion. Probably, we can have a separate discussion on the internals of Kafka. But for now, just imagine that offsets of the way unique number in conventional ActiveMQ, we have something called as a correlation ID. This is very much similar to that. This is called as offset ID. Offset ID, when consumer commits, they are maintained in a special topic, internal topic to Kafka called as a consumer offset. It is a predefined topic which is created by Kafka to maintain the offsets committed by each consumer group. So better is, in order to have performance, you have a key value per database in such cases. It could be Redis or RockDB, whatsoever. You can maintain the key value pair, whatever you have processed, then you will not have any performance problem also. Or, for that matter, even HBase, I mean, there are multiple options. I leave it to you, but you have to store that as an additional fail-safe. If your system is very critical, if you think that your system cannot cannot sustain processing duplicates, then you need to have that additional layer. Okay. Now, okay. Fine.
Heaven.
Okay. So I have a quick demo just to explain whatever we have discussed. Let me just quickly just run through the demo and then I'll execute it. So I have a consumer driver. This you can assume this as a frontliner service which is accepting input like customer ID, payment amount, email. The moment I receive this, I'm going to publish an event as a JSON. Okay, I'm going to publish an event as a JSON. Now, I have a payment processor which is a consumer for this message, not this service, this message. Remember, it is going to listen to the same topic, which is customer payment topic. And just to give some more value to this demo, I'm maintaining that data in a in-memory object, just to publish, keep publishing the data. It could be in our database in a real-time scenario. I also have another consumer, like what I mentioned earlier. This is a notification service. This notification service is going to listen to the same topic, and this will be, I'm mimicking a kind of a notification being sent out to the customer, email being sent out to the customer. Okay, in addition to that, I also have one more service, which is a fraud detection service. I will talk about it after the demo. First, let me just run my customer driver. In parallel, let me run the consumers. My customer driver is going to accept input from me. So it's asking for customer ID. Say I'll give it as say 100. It's 888. Email apc@email.com. Okay. Message broadcasted. So let me go into the payment consumer. You see that the payment has been received. Total payment which has been received till now is this amount. And from the notification, you see that notification has been sent to this email ID. This notification service is not interested in knowing the amount and all. It just needs the customer ID and the email. On the other side, my payment service is not interested to know the email ID. It is just interested in the customer ID and payment. So let me trigger one more request here. 150 is my customer ID. And amount will be guys, so these are the two payments which I received for payment and for notification. Now, this is a very simple thing, multiple consumers. I think you get this idea, right? What we are talking about. Now, what I'm going to do is I'm going to add one more key thing here. Is let me stop my notification service and payment service. I don't want them. Let this be running, or rather let me stop this also. I'm going to enable a feature. I'm going to enable fraud detection feature. Now, in the earlier case, it was one directional. I just communicated an event. The event went to payment. The event went to the broker, payment service and notification service. They started consuming. Fine. But now what I want to do is I want bidirectional communication. I want to send this information to a fraud detection topic where my fraud detection service will do some analysis and will respond back in real time, and based on that I want to show one moment. Number 200, I will assume that he is a fraud. Else, no problem. Okay. So let us see how it is working. So let me start my fraud detection server, fraud detection service, consumer. And let me start my driver. And intentionally let me give the customer ID as 200, amount is 100, email ID is going to be test@gmail.com. Sorry. So you see that the flag has got updated as is fraud, right? This is coming from my customer driver. I'm not printing it here. So what technically happens is I will get a response, because what I'm doing here, let me run through the code. After getting this entire information and converting that into a JSON, same JSON, but instead of passing it to this particular topic, which is customer payment topic in first place, I'm going to pass it to another topic, which is payment detection source topic. Okay. From where our customer driver will be listening. So upon getting that message, my customer will get this message saying that this particular customer is a fraud. So on the fraud detection side, we have detected that this customer is a fraud. On the customer side, we have detected that this customer is a fraud. So this is a very common case of producer becoming a consumer and consumer becoming a producer by itself. So we implement such methodologies when, or rather I should call it as bidirectional methodologies, where we need to have real-time responses. Now, in this case, the logic is not just a very plain simple logic, but in this case, what happens is, in general, we might refer to a Spark streaming application or other data analytics process, where this process will be offloaded to them. The data analytics process will be responding back, the response of which we will be sending on to the Kafka topic in real-time scenario. But I just want to give you an idea of how it works in real time, of how Kafka works in real time. Okay.